everyone, my name is Dmytro Gleshko, and in today's paper review, I will introduce you to a paper Segment Anything by Meta Research. And then, right before the conclusions, we will take a detour into the world of speculations and very recent papers to see some possible use cases for this model. Part 1, Introduction. In abstract, Segment Anything is a new task, model, and dataset for image segmentation. Using efficient model in the data collection loop, the authors built the largest segmentation dataset to date, with over 1 billion masks on 11 million images. The model is designed and trained to be promptable so it can transfer zero-shot to new data distributions and tasks. Authors also claim that the performance is often competitive with or even superior to prior fully supervised results. This paper and the whole Segment Anything model is heavily influenced by recent advancements in natural language processing. Large language models pre-trained on web-scale datasets are revolutionizing NLP with strong zero-shot and few-shot generalization. These foundation models can generalize to tasks and data distributions beyond those seen during training. This capability is often implemented with prompt engineering, in which handcrafted text is used to prompt the language model to generate a valid textual response for the task at hand. In this work, the goal is to build a foundation model in the field of computer vision to solve a range of problems on any data distribution using prompt engineering. To develop it, the authors address the following questions. What task will enable zero-shot generalization? What is the corresponding model architecture? And what data can power this task and model? Once again, inspired by NLP, the authors propose a promptable segmentation task where the goal is to return a valid segmentation mask given any segmentation prompt, spatial or text information. The requirement of a valid output mask means that even when a prompt is ambiguous and could refer to multiple objects, the output should be a reasonable mask for at least one of those objects. And now let's look at some details regarding architecture. The promptable segmentation task and the goal of real-world use impose constraints on model architecture, like flexible prompt support, need to compute mask in amortized real time to allow interactive use, and ambiguity awareness. Authors discovered that the simple design satisfies all three constraints. A powerful image encoder computes an image embedding. A prompt encoder embeds prompts, and the two information sources are combined in a lightweight mask decoder that predicts the segmentation masks. The same image embedding can be reused, and it's cost amortized with different prompts. Given an image embedding, the prompt encoder and mask decoder predicts a mask from a prompt in about 50 milliseconds in a web browser. To make some ambiguity aware, the authors designed it to predict multiple masks for a single prompt, allowing SAM to naturally handle ambiguity, such as the shirt versus person example. Motivated by scalability and powerful pre-training methods, the authors decided to use pre-trained vision transformer, minimally adapted to process high-resolution inputs. Image encoder runs only once per image and can be applied prior to prompting the model. There are two sets of prompts, sparse, like points, boxes, and text, and dense, those are masks. Points and boxes are represented by positional encodings summed with learned embeddings for each prompt type, and free-form text with an off-the-shelf text encoder from Clip. Dense prompts, like masks, are embedded using convolutions and summed element-wise with image embeddings. Mask decoder efficiently maps the image embedding, prompt embedding, and an output token to a mask. This design employs a modified transformer decoder block followed by a dynamic mask prediction head. To address ambiguity, the model is modified to predict multiple output masks for a single prompt. Nested masks are often at most 3D, whole object part and subpart, like in this figure. Now, to achieve strong generalization to new data distributions, it was necessary to train SAM on a large and diverse set of masks, beyond any segmentation dataset that already exists. The solution is to build a data engine, meaning co-develop the model and the model-in-the-loop dataset annotations. A complete data engine has three stages: assisted manual, semi-automatic, and fully automatic. At first, SAM was trained using public segmentation datasets. Then a team of professional annotators labeled masks by clicking foreground and background objects using an interactive segmentation tool powered by an already pre-trained SAM. Annotators were told to freely label everything and were encouraged to proceed to the next image once a particular mask took over 30 seconds to annotate. As more masks were collected, the image encoder was scaled up and the model was retrained. In the second stage, the aim was to increase the diversity of masks in order to improve models' ability to truly segment anything. Annotators were presented with images pre-filled with some confident masks and were asked to annotate any additional unannotated objects. After the first two stages, the authors collected 10.2 million masks from 180,000 images. In the final stage, annotations was fully automatic. Specifically, authors prompted a model with 32 by 32 regular grid of points, and for each point predicted a set of masks that may correspond to valid objects. As a result, their data set includes more than 1 billion masks from 11 million licensed and privacy-preserving images. Now, let's look at this absolute unit of a data set. As I've said earlier, it consists of 11 million images and 1.1 billion masks, and the average resolution of the images in the dataset is 3,300 pixels by almost 5,000 pixels, though in the released version, it is limited by 1,500 pixels. To estimate mask quality, annotators were asked to correct the predicted masks. And 94% of pairs have more than 90% intersection of reunion, and 97% of pairs have more than 75% of intersection of union. But this experiment was conducted on only 500 images, so you are welcome to be doubting. And here is the comparison to other data sets. It's pretty similar, but it's a lot bigger, and there's a lot more mask per image. Evaluation. So when training with all three stages, the automatic masks vastly outnumber the manual and semi-automatic mask. To address this, manual and semi-automatic masks are being outsampled during training by 10x. But this setup complicates training, and when using only the automatically generated mask, SAM performs only marginally lower than when using all data. Therefore, by default, only the automatically generated masks are used in training. And here you can see the comparison to similar interactive segmentation models like Simple Click, Focal Click, and Rhythm, a model that was developed by Samsung, I believe, not that long ago. SAM Oracle is a result in which the most relevant of SAM's three masks is selected. I mean, it's useful way to deal with ambiguity, but also a pretty neat way to fraud some of the evaluation experiments. To see how the model generalizes to other tasks, authors used it on tasks of different levels. The first one is edge detection, which is considered a low-level task. SAM is prompted with a 16 by 16 regular grid of foreground points, resulting in a lot of predicted masks. Redundant masks are removed, edge maps are computed using sample filtering, and SAM naturally lags behind state-of-the-art methods that learn the biases of this data set. But the results are pretty good. The second example is using SAM for object proposal. Here as well, unsurprisingly, using the detections from a dedicated model as object proposal performs the best overall. However, SAM does remarkably well on several metrics, notably on medium and large objects, as well as rare and common objects. In fact, SAM only underperforms on small objects and frequent objects, where a dedicated model can easily learn dataset-specific annotation biases, since it was trained on this particular dataset, unlike SAM. The last one is instance segmentation, which is considered a high-level task. To To do so, they ran an object detector, the same as in previous experiment, and prompted SAM with its bounding boxes. SAM is reasonably close, though certainly behind a dedicated model. On the other hand, SAM masks are often quantitatively better. When asking humans to rate masks quality from 1 to 10, we can see that SAM consistently outperforms this particular dedicated model. And here is visualization of predicted mask. Even though the dedicated model gets more points in numerical tests, the segment anything masks have clear boundaries and are more pleasant to look at. One more experiment, which is more of a proof of work, is text to mask. For this one, SAM's training procedure is modified to make it text aware, but in a way that does not require new text annotations. The key observation here is that because Clip's image embeddings are trained to align with its text embeddings, we can train SAM with image embeddings, but use text embeddings for inference. And here on the figure, you can see examples of text to masks. Now, let's take this detour into the applications and see some existing, possible, or just plausible use cases for the model. And we will begin with investigation and studies conducted on segment anything for some specific tasks. Those segment anything is not always perfect investigation on SAM on different real-world application, and segment anything model for medical image analysis. In this study, authors conducted a series of investigations into the performance of SAM across various applications: natural images, agriculture, manufacturing, remote sensing, and healthcare, analyzed the benefits and the limitations of segment anything model. And they conducted that SAM has excellent generalization on common senses. A wide range of experiments on various images validate SAM's effectiveness across different prompt modes, demonstrating its ability to generalize well to typical natural image scenarios. Unfortunately, segment anything favors foreground. SAM tends to favor selecting foreground masks. When applying SAM model to shadow detection tasks, even with a large number of clicks prompts, its performance remains poor. It is also less effective in low contrast application. Segmenting objects with similar surrounding element is considered a challenging scenario, especially when dealing with transparent or camouflaged objects. And it has limited understanding of proficient data. When applying SAM to real-world medical and industrial scenarios, it produces unsatisfactory results. That is due to the fact that both adapter, model, and users are required to possess certain domain-specific knowledge to deal with this kind of task. Also, smaller and irregular objects can pose challenges for SAM. But there is no point in being sad about your favorite segmentation model's poor performance in some particular tasks, because here comes the authors of SAM fails to segment anything, SAM adapted SAM in underperforming scenes, camouflage, shadows, and more. This study first paves the way for applying the large pre-trained image segmentation model SAM to downstream tasks, even in situations where SAM performs poorly. Rather than fine-tuning the SAM network, authors propose SAM adapter, which incorporates domain-specific information by using simple yet effective adapters. Here is the proposed architecture, and task-specific knowledge is learned and injected into the network via adapters. Using appropriate prompts to introduce task-specific knowledge can enhance model's generalization ability on downstream tasks, especially when annotated data is scarce. And when this method applied for camouflaged object detection, SAM adapter significantly elevates the performance of the model. Furthermore, quantitative results show that this method outperforms existing state-of-the-art methods. And here are some examples of camouflaged object detection with and without SAM adapter. And here are the results for shadow detection with SAM adapter. In conclusion, propose SAM adapter method, which utilizes SAM as the backbone and injects customized information into the network, can improve SAM's performance and even achieve state-of-the-art results. But wait, there's more. In Paint Anything, Segment Anything meets image in painting. Based on Segment Anything model, the authors make the first attempt to mask-free image in painting, named as In Paint Anything. The core idea behind In Paint Anything is to combine the strengths of different models in order to build a very powerful and user-friendly pipeline for solving in painting-related problems. In Paint Anything is a versatile tool that provides capabilities of remove anything, fill anything, and replace anything. It is possible by utilizing the strengths of SAM and state-of-the-art in painting and content generation models like Llama and Stable Diffusion. But wait, there's more. Track Anything. Segment Anything meets videos. Its pipeline consists of initialization with SAM, tracking with XMEM, refinement with SAM, and manual user correction. And the usages for this particular pipeline are efficient video annotation, long-term object tracking, and user-friendly video editing. But wait, there's more. Anything 3D. Towards single view anything reconstruction in the wild. Anything 3D is a reconstruction that is a framework that combines a series of visual language models and segment anything object segmentation model to elevate objects to 3D, yielding a reliable and versatile system for single view conditioned 3D reconstruction tasks. And there are billions and billions and billions, or at least 20 more projects on GitHub that utilize SAM in their pipeline. Those are Segment Anything for human mesh recovery, Segment Anything for point clouds and meshes, for NERV, a lot of labeling tools, and others. In conclusion, Segment Anything project is an attempt to lift image segmentation into the era of foundation models. Principal contributions are a new task, promptable segmentation, model, and data set that makes this leap possible. Is it a ChatGPT of computer vision? Not really. Is it a significant step in the direction of creating a foundational model? Yes. Can it be outperformed by dedicated models in specific tasks? Yes. Can its knowledge be transferred to some unpopular tasks with scarce amount of data? Yes. Are the tasks where a smart, fast, and interactive segmentation model is more beneficial for the user than some black box panoptic model? Of course. That's it. Thank you for your attention.